So yesterday we have defined series, the series in a group, which is a finite sequence of subgroups, each normal in the next. So until you get Hn plus 1, Hn in G. This is just a series. And then we have defined an omega subgroup and an omega series. So an omega subgroup is a subgroup which is invariant under the action of certain morphisms omega. So when omega is empty, is the empty set, then we have just an omega series is just a series. And the other important example that we will have, when omega is taken to be the set of inner automorphisms, one word about it in a second, then in G series is called a normal series. So in a plane series without any adjective, every subgroup is normal in the next. But when you have an in-G series, it means that every subgroup is invariant under inner automorphism. It means every subgroup is normal in G. Okay, so these are two different concepts, because just being normal in another subgroup doesn't mean it's normal in the whole subgroup. Concerning what I just mentioned, said about in G, say one may conceive different ways of having in G act on G, but since the inner automorphisms are automorphisms, so they are naturally maps on G, it is intended that they act naturally, okay? So that if you have X in G, and then what I have called the iota of G, an element in G, then its action would be just the action, the natural action of IG. What's a iota of G? It's simply the automorphism of G that takes X to its conjugate through G. Okay, so natural action. Okay. Then we were discussing, we have spoken of refinement of a series. Or remember that in the definition of a series, I have that the HI are distinct. So series cannot stumble. It is not possible to have two consecutive terms that are equal. A refinement of a series means you have a series and you insert more subgroups in a series of or an omega series between two of the terms of the previous series. And a series, if an omega series cannot be refined further, then it is called an omega composition series. There are two particular cases which I will be discussing in this course. The first is when omega is empty. So an omega series, as I mentioned before, is just a series. And then an omega series, an omega composition series in this case, is simply called a composition series. That's where the term originated, I mean, in this particular case. So this is case one, say. And case two is when omega is the set, the group of inner automorphisms. Then we have normal series. We just said that, okay, that in G series, I'll repeat this, but is a normal series. And an in G composition series as a special name, traditional name, is called the principal series. Okay. So these are perhaps the two main examples, yes, that we will be discussing: composition series, and then we'll also be discussing principal series. We'll be discussing, we finished yesterday's lecture by considering what happens when you have a composition series. Oh, by the way, this is important. In general, a group need not have a composition series. This is an example exercise. Z does not have a composition series. Remember that a series, in particular a composition series, which is just an instance of a series, is finite in length, okay? And it is a relatively easy exercise that no matter which series you take in Z, you can always insert something between two terms, okay? But I leave this as an exercise. However, if G is finite, which is the main class of groups, finite groups are the main class of groups which we will be considering, then G has a composition series. Not only a composition series, but also a principal series. By the way, Z, well, of course, under addition is an abelian group, so every series is normal because every subgroup is normal in the whole of group. So not only doesn't have a composition series, it does not have a principal series, because composition series and principal series are exactly the same. But if G is finite, that it has both. Of course, the composition series and a principal series might be different in general if G is not abelian, but it has such series simply because the process of inserting more subgroups in a series is finite, because you have just a finite number of elements, so a finite number of subsets, so a finite number of subgroups, okay? And so by working in the realm of finite groups, we are sure that these objects exist. And so what we were seeing yesterday, and I'll state it as a proposition, is let G be okay, let's say a finite group for simplicity. Let 1 equal H naught, normal in H1, and so on. Then this series, okay, we'll call it star, just so that we are able to refer of it. Then the following are equivalent. So 1 star is a composition series for a composition series for G. And let this be a series, okay? Okay, and I'll move the star to the right, to the left, so that doesn't impede this. And so star is the composition series, and 2 for every I, we have that Hi plus 1 over Hi, a quotient groups which we might consider, because every subgroup is normal in the next, is a simple group. And recall that a simple group is a group in which the only normal, as I said yesterday, is a group in which the only normal subgroups are the identity and the whole of G. Why is it so? Well, this is basically immediate, because the series star, okay, this standard series, is a composition series. If you cannot refine it further, okay? That is, if there is for each whatever here is the same here, for each I, if hi is normal in n, is normal in hi plus 1, so if there is a subgroup which is normal between two terms of the consecutive terms, or two consecutive terms of the series, then n equal hi or n equals hi plus 1, okay? Because, I mean, if you cannot refine it, the only way of inserting a subgroup in between is, I mean, hi or hi plus 1. If there were a subgroup n properly contained between the two, then you could refine it. You cannot refine it, so it means if a subgroup is in between, then it's one of the two endpoints, okay? But this, by the correspondence theorem, the correspondence theorem, there is the third isomorphism theorem, which is a basic tool of group theory, tells you that the subgroup n, which contain hi and are normal here, correspond to the normal subgroups of the quotients hi plus 1 over hi. So this means that the normal subgroups of the quotient hi plus 1 over hi, which by the third isomorphism theorem, which are of the form n over hi for n as in star star, this is star star, okay, are only, well, there are only two possibilities. Either n is hi, and this is the identity subgroup of the quotient, or the other possibility is hi plus 1 hi. Cioè, that is, as you've seen, hi plus 1 over hi has only the trivial normal subgroups, either the identity, subgroup consistence, or the identity, or the whole group. So this means that hi plus 1 is equivalent to saying that this is a simple group. Okay, saying that it's a simple group is not easy. It doesn't make the task particularly easier, because yes, there is a classification of finite simple groups. This is one of the great achievements of group theory, of algebra of the last decades. But it's a colossal work. I mean, there was a time when the proof was dispersed through at least 40,000 pages of journal articles. In the meantime, it has been shortened. It is a very complex proof, but describing the groups is not particularly complicated. There are several families and then some exceptions. But still, I mean, saying simple, it's, I mean, okay, so you can appeal to the classification if you need to appeal to this, to deal with these simple groups. So this is a composition series. It's slightly more complicated with a principal series, because, well, okay, so suppose we have a principal series, okay? Okay, let's write just this. So you have this, and then in the middle you'll have something like hi plus 1. At the end you get g, where Okay, let this be a principal series. Of G. So this means two facts. On the one side, this is a normal series. So this means that Hi is normal in G for each I. And then you cannot insert further any subgroup which is normal in G between any two terms of the of the series. So this means that then for each or every, I mean, it's the same. For each I, there is no n normal in G such that which is properly comprised between Hi and Hi plus 1. Here I'm making this, I'm describing this in the negative, okay? Which means I'm saying there is no subgroup in between. When I was talking about composition series, I was saying if there is something in between with the less than or equal to, then it's one of the two opposites, but it's the same, okay? So there is no subgroup which is normal in the whole of G, because this is a normal series. So every term has to be normal in G, which is properly comprised between the two, okay? And by the correspondence theorem, this means that there is no normal subgroup. Sorry, this is unreadable, or particularly unreadable if you prefer. No subgroup of the form n over Hi, which is normal in G over Hi, okay? Because you see, n is contained in Hi, which is normal in G, so you can consider this quotient, okay? Remember, all Hi are normal in G. There is no normal subgroup here, okay, such that this inequality becomes okay. Now we have already discussed, I mean, this is a certain subgroup. This is the identity of this subgroup. So this can be reformulated in the following way. So if L is one of the quotients of a principal series, like the one I have written down on the previous board, then L is a minimal normal subgroup the definition in a second of the group. I'll give it a name, say, okay, M, which is G over Hi. What does it mean? That is, L is normal in M. Okay, this is by the correspondence theorem. Okay, and there is no subgroup. Okay, let's call it K normal in M, such that K is greater than 1. Most of the time, I will write the subgroup consists of only of the unit element with a 1 by sort of abuse of notation. But okay, comprise properly. No, this is an L. Okay, so what does it mean to be a minimal normal subgroup? So L is normal in M, and it's also different from 1. Because remember that in a series, two consecutive terms are distinct. And there is no other subgroup normal in the whole group which is less than L, okay, and different from 1, okay? So minimal normal means it's normal, different from 1, otherwise it's trivial, and you cannot go down. I mean, if you go down, you won't find anything which is normal in the whole group. Let's give an example of this, and a good example is provided by this. Consider A4, a group of order 12, and consider its subgroup V, which is the subgroup which is consists of the identity and then the product of two disjoint, the products of two disjoint two cycles. Okay, this subgroup which is normal in A4. Okay, and is minimal normal. And it's a good example also of a phenomenon that I was mentioning yesterday. Why is it minimal normal? Because if, say, N is a subgroup that is properly contained in V and greater than 1, so this is the subgroup consisting only of the identity, well shortened to 1, then say, I mean, it is different from 1, so it contains one of these three elements. It's absolutely the same which element I consider. So suppose 1, 2, 3, 4 is in N, okay? Or let's make it this way. Let's have, I mean, to avoid a contradiction, we have a subgroup which is different from 1 and which is contained in V, and moreover, N is normal in A4, okay? So I want to prove that this has to be V, okay? I could prove that if there is something properly contained between the two, this gives rise to a contradiction, but as you know, contradictions are better avoided when you can. So you simply say N is greater than 1 and show that N has to be V. And now we'll see what happens, because this is important. In A4, you have 3 cycles, okay? 3 cycles being the product of two cycles, their even permutation. What happens when you conjugate this with 1, 2, 3, okay? And you should remember, you remember from the course in group theory that conjugating in the symmetric group is very easy, because what you do, you simply, this is a product of two disjoint two cycles, you obtain the same shape, you simply substitute to the elements that you have here, the elements in which they are mapped under this permutation. So this sends 1 to 2. So instead of 1, you write 2. This sends 2 to 3. So instead of 2, you write 3. And this sends 3 to 1. So instead of 3, you write 1. And the 4 doesn't appear here. It means it's fixed. So you obtain this. So you see, we started with this element. You obtain this one. And if you repeat, of course, the 1, 4, 2, 3 or 2, 3, 1, 4 is exactly the same thing. I mean, since N is normal, this has to be in N, because to be normal means with an element, you can conjugate with anything and you're still in N. And you do it with this. So it's the product of two disjoint two cycles. 2 is sent to 3. 3 is sent to 1. 1 is sent to 2. And 4 is left where it is. So we got this element as well. Of course, 1, 3 is the same as 3, 1, okay? So what we found that N has to be V, okay? So what I've shown, I mean, I've taken N, which is a subgroup which is normal in A4, so it's closed under conjugation, is not 1, it's contained in V, it has to be V. So there are no subgroups in between, okay? Properly contained in between. I mean, I could have started by saying this is properly contained in V and this is a contradiction, but there's no need to go for a contradiction. An important point here is that this group is abelian because it has order 4. So if you consider 1, 1, 2, 3, 4, okay? This will be normal in V. V stands for Führer group, is the Klein subgroup. Führer group means the group made of 4 elements. Of course, there's also a cyclic group, but this is. So this is normal in V, okay? So you can get, in particular, if you continue, you can get a composition series, but this, as we have just shown, is not normal in A4, okay? Is what I was mentioned the other day, that V is normal in A4, but that normality is not transitive, okay? This is normal here, but you have just shown that it's not normal in A4, because if you start with this and start conjugating, you get the whole of V, okay? So these are different things. Normality is not transitive. So we see that this minimal normal subgroups are more complicated than simple groups, because this, of course, is no simple groups, because it is abelian. It has 3 proper subgroups. I mean, one with any of these 3 elements give you a proper subgroup. And so we want to describe not exactly minimal normal subgroups, but let's give a lemma, a minimal normal subgroup is characteristically simple. Definitions coming in a second. So you have a group G, you have a minimal normal subgroup. So we just saw this is minimal normal, okay, this V, but it has normal subgroups in it, okay, proper normal subgroups. This is a proper normal subgroup of V, so it's not a simple group. But characteristically simple means, say, a group, say M is said to be characteristically simple if the only, okay, I'll first write it in terms of these omega things, because I mean, I went through to the concept of omega series and the like, so let's use them. If the only hot G subgroups of M are 1 and M, okay? Okay, so simple means that the only normal subgroups of M are 1 and M. Okay, let's say that this is different from 1, otherwise it's trivial. Okay, so this definition only applies to groups that are different from 1. Simple means that the only normal subgroups of M are 1 and M. Okay, and of course, simple means, a normal subgroup means an in G subgroup, a subgroup that is invariant under all inner automorphisms. This time, we are discussing subgroups that are invariant under all automorphisms, okay? So, in clear, let's say L, a subgroup of M, is said to be, is not said to be, is a not G subgroup, also known as a characteristic subgroup of M, if but let's say, okay, if L phi is equal to L for every automorphism of G. So normal means that L is sent to itself by every inner automorphism, okay? Whereas characteristic, which is the same thing as an hot G subgroup, means the L is left invariant, is sent to itself by every automorphism of G. Okay, so characteristically simple means that the only So let's rephrase it. So M is M different from 1 is characteristically simple. I'm repeating the definition I gave. If the only subgroups the only characteristic subgroups of M are 1 and M. And once more, characteristic, which is exactly the same thing as hot G subgroup, okay? These two terms underlined in red are exactly the same thing. I mean, there are multiple names for the same thing. I mean, characteristic is the name that you will find more often. Characteristic means the only characteristically simple means that the only characteristic subgroup of M are 1 and M. Okay, fine. But characteristic means invariant under all automorphisms. Of course, it might have normal subgroups, so as we will see soon. Okay, so why does this lemma hold? And the reason why this lemma hold is, well, I could have used another lemma, say a lemma which proves the lemma. Let G be a group, and let let's say C be a subgroup of N, which is normal in G, okay? So we just saw with an example that if C is normal in N, it doesn't mean that it's normal in G. But if C is characteristic in N, then C is normal in G. So normality is not transitive. C normal in N, normal in G doesn't imply that C is normal in G, but if C characteristic in N, then C is a normal subgroup of G. Why is it so? So let's prove this first of all. This is because you see, we'll see with an example. We see in the previous example how this works. Let G be any element of G, and C be an element of C, okay? So we want to prove that C is normal in G. So I consider its conjugate, okay, to be proved that this is in C. But this is C to which I have applied iota of G, okay, the inner automorphism. This is just the definition of the inner automorphism. Now, iota of G, okay, iota of G is an automorphism of G, but since N is normal in G, iota of G restricted to N maps N to N, okay? So you know that G being normal means that this is in N. So once you restrict this to N, you get an automorphism of N, okay? There is the usual problem with restriction. Restriction means that you only consider iota of G applied to elements of N, but you don't know where it ends, okay? It might be that it doesn't end in N. If N is not normal, this will be different from N. But N is normal, so this is N. So you can restrict this to N and you obtain an automorphism of N. Because iota of G is a morphism, so it's still a morphism when restricted to N. And the point is, so since C is contained in N, C to the iota of G is exactly the same thing as iota of G, C to the iota of G restricted to N, because C is a subgroup of N, okay? And since C is characteristic, this is in C, okay? So the idea is you conjugate an element of C by an element of G. This operation is an automorphism of N. Your hypothesis is that C is invariant under the automorphism of N, and then this means this element is still in C, okay? just to give you an example, an instance of this lemma, I'll leave it for a second here so you have time to write. This is what happened when we are considering V normal in A4, okay? Well, not exactly, but you will see in a second. Okay, so just to give you an example, so while it's not exactly of a characteristically simple, but it's the same. So you have V normal subgroup in A4. If you consider iota of 1, 2, 3, for instance, this is an automorphism, an inner automorphism of A4. But since V is normal in A4, iota of 1, 2, 3 restricted to V is an automorphism of V. This is what we have seen, that this automorphism send this to 2, 3, 1, 4, and then sends this to 1, 3, 2, 4, and then we could see that it send this back. But note that this is an inner automorphism of A4. This is an automorphism of V, but this is not an inner automorphism of V. As V is abelian. And so in an abelian group, inner automorphism of conjugation are trivial. There's only the identity, okay? So you see that you have an automorphism of A4, which is inner. When you restrict to V, you obtain an automorphism of V, but this is not, it's not inner anymore in V. And that's the reason why you can have normal subgroups in V, but not characteristic subgroups, okay? So with this lemma, if a characteristic in normal, okay, let's use the pointer, just a second. The pointer should be this one. So, no, it's not. Oh, yes, this one. C, characteristic in N, normal in G, means that C is normal in G. Okay, characteristic in normal means normal. This is the way of recalling this, and then this shows that a minimal normal subgroup is characteristically simple. Why? Because if you have a normal subgroup and you have a characteristic subgroup in it, then this is normal in the whole of G. If this is minimal normal, you cannot have any characteristic subgroup in it. Okay, but let me write this down. So no, next. Okay, so say lemma 2 implies lemma 1. Let me label these lemmas with numbers. So this is lemma 2, and this is lemma 1. And the reason being, if M is minimal normal, and C is characteristic in M, then by lemma 2, C is normal in G. So the only possibilities are C is 1 or C is M, because we had assumed that M is minimal normal, meaning that the only normal subgroups which are contained in M and are normal in G are 1 and M, okay? So what we found, let's go back in a second, and then we'll get back to this. A minimal normal subgroup is characteristically simple. Characteristically simple means that the only characteristic subgroups are 1 and M, okay? And so because of this, so remember that what we found is that in a principal series, each of these quotients between two consecutive terms of a principal series give you a minimal normal subgroup of this quotient. Okay, so the quotients of a principal series are minimal normal subgroups of a certain quotient. So these are characteristically simple groups. And so to understand principal series, okay, we are going to describe let us describe finite characteristically simple groups. Not finiteness, okay? We are dealing with finite groups. So let M be such a group. Recall different from one such a group. So we'll play around with this concept, which is important. Characteristically simple group means every time you have a subgroup different from one, which is invariant under all automorphisms, it has to be the whole group, okay? Consider the first case in which, just a second. Well, okay. Okay, let them be such a group, characteristically simple, and let N be a minimal normal subgroup of N itself. Because we are assuming that this has no characteristic subgroup, but it might have normal subgroups, okay? The standard example is provided by V normal in A4, okay? This is minimal normal, say, but it has normal subgroups, okay? Which are not normal, which are normal in V, but are not normal in A4. So let N be a minimal normal subgroup of N. There are two possibilities. First possibility, N is abelian. Okay. If N is abelian, then you recall that N is the product of its Sylow P subgroups. For various primes, for the primes pi that divide the order of N. Okay, this is not really necessary what I just said, but let's put it this way. If P, this group is finite, so we can appeal to Sylow subgroup. If P is a Sylow P subgroup of N, okay, for some prime P, which divides the order of N, then, I mean, every subgroup is normal here, then P is unique, okay? Recall that the Sylow subgroup in a group, in a finite group, is unique if and only if it's normal, okay? So N is abelian, so every subgroup is normal, so this is unique. And then you see, but then P is characteristic in N, okay? The reason being that if you apply any automorphism, so what's P? P is by definition, say, if the order of N is P to the E K, okay, where P is a prime, we said is a prime and P does not divide K, and E is greater than or equal to 1, then P is the unique subgroup of order P to the E, okay? But automorphisms preserve orders. There are bijections. And so let's put it this, if like this, if phi or phi is an automorphism of n, then p to the phi preserves as in order of p, so p to the phi equal p, okay? So let's see. I've taken M, which is a characteristically simple group. I've taken a minimal normal subgroup, and I had assumed it's abelian, okay? Then I have seen that if I take a CLOP subgroup of N, this is characteristic in N. And so you see, let me write this. We have P characteristic in N, which is normal in G, okay? This implies that P is normal in G by the lemma I just described. But N, I had taken N to be a minimal normal subgroup of N. And here I have a subgroup which is different from 1, and which is contained in N and then normal in G. So it follows that N is P. So if N is abelian, it has to be a P group, okay? A CLOP P subgroup, okay? So we have found that that N equal P is a P group, is an abelian P group. So a group of order P to the E. Now, since N is abelian, well, by Cauchy or by anything, there are elements of order P in N, okay? Of course, yes, but if you want, it's Cauchy's lemma, but it's easier than that, because if this is different from 1, it will have an element of a certain order, P to the K, you raise this to the P to the K minus 1, you obtain an element of order P, but let's use Cauchy. So it has an element of order P. So the subset of N, which is an abelian P group, given by the X in N, such that X to the P is 1, is different from 1, okay, because by Cauchy there are elements of the P, and it's a subgroup. It's a subgroup because N is abelian. This is my assumption. Later I'll see what happens when N is not abelian. And so why it is important that N is abelian, because if you have a product of two elements to the P, usually this will give rise to xy, 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 and you cannot normally exchange to x and y, but since it is abelian, this will be xp, yp. So if x to the p is 1 and y to the p is 1, then the product is also, raised to the p is also 1, okay? This is abelian, and it is characteristic. No, let's call this Q. Well, bad name, but important, doesn't matter. And the Q is characteristic in N. Why is it so? Because characteristic means that if you take any element of Q and you apply to it an automorphism, you are still in Q. And the reason why Q is characteristic in N, because automorphisms preserve the order of an element. This is a relatively simple argument, which I'll leave an exercise. Essentially, you can do it like this. You can prove that if you have an element of a certain order, N in a group, and you apply a homomorphism, then the image under this homomorphism will have order dividing M, okay? If you have an automorphism, it has an inverse. So there are two inequalities. One, say, M, the order in the image divides M and vice versa. So M equals the order of the image, okay? So preserve the order. So this is characteristic. And once more, since we have taken n minimal normal in capital M, this means thus n equal q is a so-called elementary abelian P group. So abelian means abelian, P group means a group of order power of P, and elementary means exactly this. All x to the P is 1 for all x in n. Okay. And there is an important fact that is dealt with in the Teoria dei Gruppi course. If it's necessary, just let me know and I can review it. An elementary abelian subgroup, an elementary abelian P group, is really the same in a specific sense than a vector space over the field Fp with P elements. Meaning that that if you take an elementary abelian group, P group, you can give to it a structure of such a vector space. If you have such a vector space, then its additive group is an elementary abelian P group. And moreover, the important thing that the out Q, the automorphisms of this elementary abelian P group are nothing else coincide with the invertible linear maps. On this vector space. Let me know, I mean, write me or tell me whether you need to review this part, which is quite useful because, I mean, usually determining all automorphisms of a group is not an easy task. But for elementary abelian P group, you reduce to linear algebra, which is also always something interesting to do, okay? I mean, always useful because, I mean, once you have a linear algebra, you have matrices and so on, and you can do a lot of things, you know a lot about this. So this is the first situation that we have dealt with. That is, we have taken a group which is characteristically simple, okay? And we have taken a minimal normal subgroup of M. Okay, yes. Just a second. Yes, so since n was characteristically simple, we have found that, just a second. Okay, we have found this. Yes, and what we have found, I forgot to mention this, that this n, just a second. Well, in any case, what we have proved is that if M is a characteristically simple group and a minimal normal subgroup of M is abelian, then more or less, I mean, no, for what we have proved, more or less, I mean, is that if M is characteristically simple, and the minimal normal subgroup is abelian, it has an abelian minimal normal subgroup, then M is an elementary abelian P group. For some prime P. This is something that I'm not completing in the argument, but this is what we proved in practice. So this is the first case when it has an abelian minimal normal subgroup. Okay, so the second case is when we are still with M characteristically simple. And so if it has an abelian normal subgroup, then we know how to do. If all abelian, if minimal normal subgroups are abelian, I can apply this and suppose that M has a non-abelian minimal normal subgroup N. Okay, we'll see later that it has to be simple, but we'll get to that. So it's not abelian, because if it's abelian, we have seen how we deal with it. Good. So N is normal in M. And there is an important fact that for each automorphism of M, N to the phi is also normal in M. Let's do the calculation first, and then we'll see that there is a more general fact in it. So you have a normal subgroup, you apply an automorphism, and you're still a normal subgroup. And the reason is the following. So we have N normal in M, and we have an automorphism of M. So I apply to this, say, iota of G for some G in M, and want to show that this is, is still N phi. So what's this? This is N to the phi conjugated with G, okay? So you have a phi here, pull phi out. Of course, N is now naked, it has no phi anymore, but I mean, you have pulled something that is not there, so you compensate. There is the classical, say, adding and subtracting, okay? I mean, if you read it from this to here, from here to here, you see that it works because you apply phi here. This is an automorphism, so it distributes, and the phi inverse phi cancel, and you obtain N phi here, and once more phi inverse phi again cancel. Okay, so what we have found here, you have found N conjugated by this element. Okay, let's put it here. So this N conjugated by which element? G to the phi minus 1, and then phi. But N is normal in M, so if you conjugate N by anything, you get N. Okay, so essentially what I've done, I've switched IG, the iota of G to the left. There's a price to pay, this phi inverse, and so this proves that N phi is normal in M. But what's behind this calculation? There is a usual fact. Remember that in of G, the inner automorphism group was obtained as an image of the iota morphing from G to G that sends G to the conjugation by G, okay? So iota of G, the image, is called the inner automorphism, all automorphisms of this. And this is, of course, a subgroup of G, of what G? I mean, because this is a morphism, a homomorphism, which are called a morphism for short. This is a morphism, so its image is a subgroup. Of course, its kernel, the center, is normal in G, but usually you cannot say anything about the normality of an image of a subgroup under a homomorphism. But what we have is that in G is normal of G. Okay, and how do you prove this? The proof is very simple, because you take G in G, you take phi and automorphism of G, okay? And you want to compute this conjugate to be proved that this is in G, okay? This, if you want, is composition of maps in the automorphism group, okay? So the operation in the automorphism group, the automorphism group is composition of maps. It's simply maps which are then morphisms. And you want to prove that this is an inner automorphism. So what you do, you apply this to an element X, and you get. So I write these maps on the right. So I apply these maps one after the other. So first I apply this, and then I conjugate. And then I reapply phi. And you see it's more or less just with the different notation what I had a moment ago. So this is G phi 1, X, because phi inverse and phi cancel, okay? What I've found, this X conjugated by G phi. So I have conjugated the inner automorphism iota of G, and I obtained another inner automorphism. So this is, I proved this. So I proved that if you conjugate in the automorphism group the inner automorphism induced by G by phi, you obtain another inner automorphism, which is G phi. And if you look closely, I'll get back to this board in a second. The calculation here is exactly the same, except that the phi is in a different place. So the main point is exactly this, that the inner automorphisms are normal in the automorphism group. And the calculation is simply like this. I mean, note just the basic fact. I want to prove that these two maps are equal. So I compute them on X in G. Since these are maps on G, automorphisms are maps on G, I compute them on an element of G, X of G, and I have to prove that they give the same value. That's what I've done here, okay? Standard procedure. Good. So, what we have found? We have M characteristically simple, N normal in M, a minimal normal subgroup, non-abelian. And now what I've seen is that all images of N under phi are also normal in M. Okay. Now, I want to prove that there are automorphisms, phi1, the identity automorphism, phi2, phi k, say, automorphism of G, such that M is the direct product of N times N phi2 times N phi k, okay, where N is N phi 1. So it's a direct product of some of this N phi, okay? And I proceed by induction because if M is N, you are done. It's a trivial case when K is 1. Otherwise, suppose I have found phi1 equals 1, phi2, phi, say H, automorphism of G, such that, say, the subgroup generated by N phi 2, sorry, N phi H is a direct product. Okay, so this is the subgroup generated, and you remember, since all these subgroups are normal, the subgroup generated by this is just the product of them. Okay, it's this is part of the second isomorphism theorem, which tells you that if you have two subgroups and one of them is normal, then the subgroup generated by them is their product. Okay, in general, it's the product of two subgroups won't be a subgroup, But if one of them is normal, here all of them are normal, the product will be a subgroup. So suppose I've already done this for a certain steps, but this is still not M, okay? Good. Then note the following, that if you consider the subgroup of M generated by all n phi, when phi is not G, then this is characteristic in M. Okay? And of course, it's different from 1. Why is it characteristic? Yes, because simply because if C is any automorphism of G, then if you apply this to this subgroup generated by this, you can pull the psi inside. And we know that in a group, if you multiply by a fixed element, you still obtain, of course, all the elements of the group. So this is the original group, okay? I mean, it's just the fact that multiplied by an element in a group is a bijection, so of the group. So this, you see, if psi is any automorphism of G, this is sent to itself. So this is a characteristic subgroup in M, and then it has to be the whole group of G. Okay, so since M is characteristically simple, you need you obtain that this is the whole of M. So remember, so far I have this I mean, the induction step is n, okay? N, of course, is a trivial direct product with only one factor. Suppose I've done already h factors, okay? So if m is already this, we are done. Otherwise, if this is less than m, because these subgroups, the subgroup generated by the images under the automorphism group of n is characteristic in M, and then is n. Since this is not M, there will be an automorphism phi of G such that n phi is not contained in the subgroup generated by n phi 2, n phi h. Okay? Because our assumption is that this is proper in M, and M is generated by this, so it's not possible that all of these are contained here. But remember, we have shown that all these are normal in M, and moreover, since N was minimal normal, N phi is also minimal normal. Automorphisms preserve properties of groups, so N phi is also minimal normal in G, in M. And so what could, let's give a name to this L for simplicity. So L is a product of normal subgroups, so it will be normal in M. So N phi intersect L will be a normal subgroup of M contained in N. But actually, okay, contained in N phi, okay? And it cannot be N phi, of course, because if the intersection of N phi with L is N phi, it means that N phi is contained in L, okay? And so there is no possibility, since this is a minimal normal subgroup, and this is a normal subgroup contained in N phi and different from N phi, this intersection has to be 1. So if you consider the subgroup N phi L, okay, which is then generated by L was generated by N and phi 2 and so on, and phi H and phi, okay? So this is, since these are normal, this and phi L, okay? And the second isomorphic criterion, the intersection is 1. And so this means that the group generated by this, it's a direct product. It's a definition, it's the standard characterization of the direct product. You have a subgroup generated by these two normal subgroups, with intersection is trivial, then the subgroup generated is isomorphic to, or say it's the internal internal direct product of these two. But L was the product of this, so what you find, let's write, let's begin from here. I've reverted the order, but it's isomorphic. This is no problem, and phi. So you see, we had assumed that we already had a product of H subgroup of this form, and I have added one. Okay, so proceeding by induction. We'll find that M is the direct product. I mean, I keep repeating this until I hit, sorry, this is normal. This is a direct product. Okay, so it's a direct product of this. And this tells you immediately something. This is a minimal normal subgroup of M, but since this is a direct product, if K is normal in N, so this is normal here, but N is, I mean, since this is a direct product, then it's easy to see that K is normal in M, okay? And so this means since N is minimal normal, since N is minimal normal, this means we have that N is simple. Simple non-abelian. Okay? Because every subgroup which is normal in N commutes with all of this. I mean, in a direct product, each factor commutes with the others, and once a subgroup is normal in N, it commutes with the others, so it's normal in the whole of N. So what we have found the following, that, so summing up theorem, if M is a finite, characteristically simple group, okay, and remember, these are important because these are the factors in a principal series, then M is a direct product of isomorphic copies of a finite simple group, of a simple group is finite. And there are two possibilities. Either M is, let's say, Cp times Cp, where Cp is cyclic of order P. And so the simple group in this case here, the simple group is abelian. It's Cp. In an abelian group of all subgroups are normal, so the only simple abelian group are cyclic of order P, or M is isomorphic to S times, okay, let's write it like this, where S is a non-abelian simple group. Okay? it's better to distinguish the two cases because you'll see when we show the converse, they are really different. So what I want to show to finish the lecture today, this is an implication. If M is characteristically simple, then it's either an elementary abelian group, okay? This is an elementary abelian pregroup. If you wish here, I'm appealing to another result given in Teoria dei Gruppi, that is the fact that every finite abelian P group is a direct product of cyclic groups. And so elementary abelian means that these cyclic groups are all cyclic of order P. So we have these two cases, but we have to show the converse, that if you have a subgroup of this or this kind, then it's characteristically simple. So let's see the converse briefly. So let's consider case one, M, an elementary abelian. So an elementary abelian P group. We want to show that it's characteristically simple. We want to show. Okay, that is, it has no proper non-trivial characteristic subgroup. And here the point is that, as I said, if M is order P to the E, okay, then hot M, as I hinted to before, but if you need, I can go through the argument. Then M is really a vector space of dimension E over the field with P elements. And so hot M is really given by yes, EP. This is the linear group. What this means, invertible. E times E matrices over the field FP, the field with P elements. And now to prove that this is characteristically simple, you just need to use a standard fact from linear algebra that if V and W are two vectors in M, both different from 0, okay, then there is an element. No, sorry, this is unreadable or particularly unreadable. An element, an automorphism, but a matrix such that which takes one to the other. That's an easy fact in linear algebra because you have V, which is different from 0, so you can complete it to a basis, add E-1 elements to make a basis. Same thing with W. W is different from 0, so it's part of a basis. And you know that there is an invertible linear maps, which maps the first basis to the second basis, so it maps V to W, okay, in particular. So it does more than that, but, and this shows that the only characteristic subgroup is M itself, because if you have any a characteristic subgroup which contain V, it has to be invariant under phi, so you cannot go out of it, okay? I mean, every W in M different from 0, it has to be inside here because if it's characteristic. I'll leave you to complete this. And let me show you what happens when you do the second case. Okay, so this time M is the direct product. Okay, let's write it like this. Okay, where SI are isomorphic non-abelian simple groups. And again, I want to prove M is characteristically simple. So there is, it has no characteristic subgroups. And okay, so what I'll be doing is to do the following. Let L different from 1 be a normal subgroup of N. So first of all, I'm discussing what I can say about a normal subgroup. Of course, characteristic means the characteristic implies normal, okay? Because yes, I hope I've mentioned this before, because characteristic means hot G subgroup, okay? And normal means in G subgroup. So a subgroup is characteristic if it's invariant under all automorphisms. Among the automorphisms of G, you'll find the inner ones, okay? So if a subgroup is invariant under all automorphisms, it's of course invariant under the inner ones. So let's first discuss the normal subgroups. And what I'm doing here is a particular case of one of the possible seminars about Krull-Schmidt, which, well, you'll find the references in the list of seminars. This is a particular case. It has to do with the uniqueness of the compositions, okay? So, for instance, roughly speaking, I mean, you have a direct product in two forms. Are they related? You have the same group written as the product, the direct product in two forms. Say, okay, direct product of a certain form, but look at the list of seminars. Okay, so you have a normal subgroup of N, which is different from 1. If it's different from 1, it has to contain, of course, an element which is different from 1. This is a direct product, so you can write the elements as k-tuples. If a k-tuple is different from 1, it means that one of the components will be different from 1. So without loss of generality, just for simplicity, I suppose that the first component is different from 1, just for the notation. But of course, it could be any component. So suppose S1, S2, Sk is in L with S1 different from 1. Okay? And so this is normal, okay? But since these SI are non-abelian, there will be, just a second. Oh, yes, it's simple. Yes, okay, sorry, I had to say something more. So S1 is different from 1 and is in S1, which is a simple non-abelian group. So S1 does not belong to the center of S1 because the center of a group is a normal subgroup, actually a characteristic subgroup, and this being simple, this has to be 1, okay? So it cannot be in the center. Recall that the center of a group, let's call it G, is the set of G in G, such that Gx equal Xg for all X in G. Okay? So since this is a non-abelian simple group, the center is 1. Of course, if it's an abelian simple group, it's cyclic over the P, is abelian, so the center is the whole group. But since it's non-abelian, the center cannot be the whole of group. Okay? Let's put it like this. Zg equal G means same thing, G is abelian. Okay? So you have this S1 here, and it's not in the center. Then, if it's not in the center, then there is X in S1 such that S1X is different from XS1. Or in other words, the conjugate is different from S1. Okay, I have just taken the X inverse on the left side. But then consider the following. So we have S1, S2, Sk, which is in this L. Okay, and then I can conjugate. No, well, okay, let's take the inverse. So these are all inverses, okay? And then I can take the conjugate of this by x11, okay? And this, again, will be in L, because L, you see, L is normal in M, okay? What do we get here? Well, okay, the inverse of an n-tuple, of course, is the n-tuple of the inverses. And then I conjugate, the ones do not make any difference, so you have this. This is a direct product, so you do operation component-wise. And you see that all other terms cancel, okay? Okay, and this is different from 1. Because this is different from this one. So this is equivalent to saying, of course, that S1 inverse, X inverse, S1X is different from 1, okay? So what we find here, this is an element which is in S1 times 1 times 1. Okay, so what we found that, there is this element which is different from 1, which is in S1, say, the first component, and in this subgroup, normal subgroup in M, okay? So what I've found, and then I'll finish, what I found that S1, which is the first component, intersect this L non-trivially, okay? But this is, as L is normal in M, this is, of course, a normal subgroup of S1. S1 was simple, so the only possibility is it cannot be, is not 1. S1 is simple. So what we found is that it has to be S1. That is, S1 is contained in L. I did this for convenience with S1, but what we have proved so far that if L is different from 1 and is normal in M, then L contains Si for some I. And I'll finish this next time by showing that, so far L was just normal, but if you take L to be characteristic, then if contains one of the Si, then it has to contain all of them. The reason is that M is a product of these simple groups which are isomorphic, and we'll show the relatively easy fact that there is an automorphism that permutes all of them. So once you have one of them in a characteristic subgroup, it has to contain all of them. Okay, that's all.